Hi there. I'm glad you've found your way into this small pocket of quiet. Somewhere beyond the roofs and trees, the night is carrying its usual traffic of starlight old photons, crossing impossible distances, all moving at the same relentless pace. For a long time, we've treated that pace as the universe's ultimate speed limit, the one rule everything must obey. But tonight, we're going to sit with a softer, stranger question. Is that really the whole story? Could the cosmos be hiding ways of moving, stretching, or folding space that slip past what light alone can show us? We'll wander slowly through ideas of limits and loopholes, of signals and shadows, and of what fast even means when space itself can change. If drifting through questions like this brings you a bit of calm or curiosity, a quiet like and a gentle subscribe, help others find this corner of the night too, only if it feels right. For now, we'll just begin. We begin quietly with something you already know, even if you don't usually stop to name it. The soft glow on your screen, the faint outline of furniture in the dim, the way a city leaves a pale memory against the clouds at night, that's all light. It's so ordinary that it feels like part of the background, like air or gravity or time passing. But underneath the glow and the color, light is mostly one simple thing: motion. It is what happens when something ripples through the fabric of the universe at a very specific pace, over and over, never late, never early. When people talk about how fast light is, the numbers sound almost made up. In the time it takes you to say 1 Mississippi, a beam of light could circle Earth more than 7 times. The light leaving the sun takes around 8 minutes to reach us, even though to your eyes, the sun looks as if it's just hanging there in the sky. We give this pace a number about 300,000 kilometers every second and call it the speed of light, as if it were just another fact to memorize. But it is more than a fact. It is a rule. So far, in every careful experiment and every wandering of our curiosity, nothing has outrun that rule. No particle with mass, no burst of energy, no rocket or star or exploding galaxy has been caught moving through space faster than light does. At first, that might sound merely impressive, like saying someone is the quickest runner in the world. But the more deeply you look, the more it feels different from that. Light is not just the current champion, it's the finish line itself. The universe seems to have written a speed limit into its foundation, and that limit is the pace at which light travels. That idea, that there is a hard ceiling on speed, did not come from a hunch. It grew slowly, out of questions that wouldn't quite go away. At the beginning of the 20th century, Albert Einstein took those questions seriously enough to let them rearrange everything. Before his work, most people assumed that light must behave like everything else. If you watch a car drive past while you are standing still, you measure one speed. If you are in another car, going in the same direction, the passing car seems slower. Speed depends on who is looking, on how quickly they themselves are moving. By that logic, you might expect light to follow the same rule. If you ran toward a beam of light, you might think you would see it approach just a little faster. If you raced away from it, maybe it would seem just a bit slower. The numbers ought to add and subtract the way we are used to. But when people tried to test this carefully, the universe gave a different answer. No matter how you move, no matter what direction you choose, if you measure the speed of light in empty space, you get the same number, always. Einstein decided to believe the measurements. He treated that one stubborn fact as non-negotiable. The speed of light in a vacuum is constant for everyone, everywhere, no matter how they are moving. If that is true, then something else has to give. The something turned out to be almost everything we thought we knew about time and space themselves. Instead of forcing light to adjust to our expectations, the universe lets light stay steady and bends reality around it. In this view, time is not a single, universal ticking that everyone shares. The faster you move, the more gently your own time stretches. Clocks on fast-moving ships would really run slow compared to clocks left behind. Distances along the direction of motion would really shrink. Events that seem to happen at the same moment, for one observer, might happen in a different order for someone rushing past. All of that strangeness flows from one quiet rule: light will not change its speed to please you. It keeps its pace, and space and time reshape themselves so that this can remain true. There is another twist. If you try to push something with mass closer and closer to that ultimate speed, it resists you more and more. Each extra bit of acceleration costs more energy than the last. To actually reach the speed of light would require an impossible amount of energy, a kind of infinity that nature never seems willing to supply. For us, and for anything made of ordinary matter, light's speed is a horizon we can approach but never cross. All of this might sound grand and remote, yet it sits quietly beneath everyday life. When you walk down a street or watch clouds drift across the sky, you never feel your time stretching or your length changing. The speeds we move at day to day are tiny compared to the cosmic limit, so the effects hide in the decimal places, yet they are always there underneath, written quietly into the way particles move and signals arrive. Light's pace is like a rhythm line in a song that never stops. Speed is always a relationship. How quickly one thing changes its distance from another. You measure it by choosing 2 points and asking how far and how long. If the stage the motion plays out on begins to shift under your feet, that simple idea starts to bend, and the question of what counts as fastest becomes softer around the edges. To see how, you can picture the universe as a great, dark fabric, sprinkled with galaxies like tiny, glowing stitches. For a long time, people assumed that fabric was still, a silent backdrop where everything else moved. Then, evidence began to collect that the backdrop itself was stretching, not like an explosion with shrapnel flying outward through empty space, but more like a vast balloon, very slowly inflating, carrying its painted dots farther apart, without any of them needing to move on their own. When cosmologists say the universe is expanding, this is what they mean. The galaxies are mostly just staying where they are, like leaves frozen in ice, while the ice itself grows and thins between them. From our point of view, that stretching shows up as a drift. Distant galaxies look as if they are rushing away from us. The farther they are, the faster they seem to retreat, because there is more space between us and them to stretch. Here is the strange part. For galaxies very, very far away, that apparent retreat can be faster than light. The distance between us and them can grow in such a way that, if you tried to follow it like a speed on a dashboard, it would exceed light's limit. At first glance, that sounds like a violation of everything we just whispered about. But nothing is breaking the rule, because the rule is subtle. It says nothing can move through space faster than light. It does not say space itself must sit still. If the fabric is stretching, it can carry 2 points apart at a rate that no traveler could ever match. It is like standing on a treadmill that gradually speeds up under your feet. You can walk, you can run, but the belt can still carry you backward faster than your legs can push you forward. The cosmic speed limit applies to your feet, not to the machine itself. In the same way, galaxies are not racing through the void faster than light. The void is simply widening between them. To explore those possibilities, physicists sometimes give names to things we have never seen. One of those names is tachyon, a hypothetical particle that would always move faster than light and could never slow down to match it. We have no evidence that such particles are real. They are shapes that appear in certain equations, hints that our descriptions might be incomplete. Whether or not they exist, they let us ask a quieter question. Are we sure that light's limit is a law of all reality, and not just a rule of the part we can touch? What we do know is that almost everything we learn about the universe arrives on the back of light. Telescopes listening to radio waves, watching visible colors, catching X-rays or gamma rays are all, in the end, timing how those signals reach us. Even in particle experiments, the traces we record are small flashes in sensors or pulses in circuits. Our rulers and clocks are built from light's behavior. They cannot get ahead of the very thing they rely on. So if there were something that moved faster than light, it would be like a whisper that finishes before sound has even been invented. Our usual instruments would never hear it. We would not see it streak across a detector or watch it slide across the sky. At best, we might notice that some patterns do not quite make sense unless a hidden influence has passed through, the way you might guess that a bird has flown by from the startled rustle of leaves, even though you never saw its wings. That thought opens a different path. Maybe the universe holds forms of connection that are not about racing signals at all. Instead of imagining a particle trying to sprint past light's limit, you can imagine a link that does not travel from here to there, but simply exists between here and there. No journey, just a shared state. Quantum physics brings us a taste of this with something called entanglement. Two particles can be prepared so that they form a single shared system, even when they later drift far apart. Measure one, and you instantly know something about the other, no matter how much distance lies between them. To Einstein, this felt unsettling enough that he called it spooky action at a distance, as if nature were sneaking information across the universe faster than light could move. Over time, experiments have shown that entanglement does not let anyone send a usable message faster than light. We cannot steer the outcome of a measurement at one end in a way that someone at the other end could read as a code. The cosmic limit still holds. Yet the existence of this deep, non-local connection hints that our usual ideas of here and there, of before and after, are not the whole story. If that is true, then perhaps the question changes shape. Instead of asking, can anything move faster than light? We might ask, is motion the only way things can be related? Light is bound to the notion of traveling from point A to point B, carrying energy and information along a path. Entanglement suggests that some relationships do not need that kind of journey. They are woven into the setup from the start, like two notes written into the same chord. Around the edges of modern physics, there are other ideas that tug on this thread, extra dimensions beyond the three we can picture easily, hidden structures in space-time, new ways of thinking about cause and effect. Many of them are difficult to visualize. They live more comfortably in equations than in bedtime stories. But even in this softer form, they offer a simple comfort. We do not know everything yet, and that is okay. Our limits are not proofs that nothing lies beyond them. They are just reminders of the tools we are using. Right now, light is already busy at its usual work. Photons are leaving distant stars, crossing gulfs of darkness at their steady pace. Some left before anyone you've ever heard of was born. Some will still be on their way, long after your name has faded from memory. A few of those travelers will eventually slip through our atmosphere and brush the back of your eye or a telescope's mirror. When they do, they will be right on time, exactly as fast as they are allowed to be. Because their speed is finite, there is always a delay. When you look up at the night sky, you never see anything as it is now. You see it as it was, the light carrying a memory of its source from years or centuries ago. Some of the stars whose light reaches you this evening may already be gone. In that way, the speed of light keeps us slightly out of step with the universe's present, living inside a moving archive of messages sent long ago. Every glance at the sky is a small kind of time travel, not into the future, but gently backward. What we can say, without stretching beyond what we know, is that in the world we can touch and measure, light holds the record. It defines the outer edge of what can be signaled, the maximum pace at which one event can influence another through space. It gives us a ruler and a clock and a way to order things, while quietly reminding us that our view is always partial, framed by the very signals we use to see. Beyond that frame, there may be more, or not. For now, it's enough to sit with a single steady idea. Every soft glow you notice, every gentle reflection, every star that pricks the dark is a trace of motion at the universe's top speed, carrying pieces of information from one place to another. Light is both our messenger and our limit. Fastest here is more than a race. It is a boundary, a promise, and perhaps just beyond it, an invitation we haven't yet learned to read. And every time you look up into the sky, even for a moment, that invitation is already at work. The stars, the hazy band of the Milky Way, the soft glow above a city, they aren't showing you how things are right now. They're showing you how they were. Light is generous with beauty, but it always arrives late. What reaches your eyes is a record, not a live broadcast. Bright, delicate, and delayed, a quiet reminder that even at the universe's top speed, we are always seeing the past. That's true even in the small spaces of your own life. Light doesn't cross a room in zero time. It takes a tiny sliver of a second to move from the lamp to the wall, from your screen to your eyes. To go from one side of the planet to the other, it needs a fraction of a second more. When you talk to someone half a world away and feel that faint pause before their smile lands on your screen, part of that stillness is just light and the signals built on it doing the best it can. It's not that light is slow. It's that even our little world is already wide enough that instant is never truly instant. So the question that keeps tugging at us lingers. Is light really the fastest thing there is, or only the fastest thing that lets us know it exists? To even touch that question, we have to sit for a moment with what light actually is, not as a metaphor, but as the universe seems to treat it. In the language of physics, light is made of photons. You can picture them as tiny packets of energy, little quanta that sometimes behave like particles and sometimes like waves. In the quantum world, those categories blur together. This and that refuse to stay separate. Light isn't neatly one or the other. It's both, and also something deeper we don't have an everyday word for. What matters for this story is one simple fact. Photons have no mass, none at all. They don't carry weight, they don't rest. That turns out to be everything. In our best understanding of nature, anything with zero mass has no choice about its speed. It must move at the speed of light. There is no slower setting available. It's not that photons decide to race as fast as possible. Their existence is tied to that particular pace. No mass means no sitting still, no gentle rolling start. It means always moving, always at that same ultimate speed. Everything with mass lives on the other side of that rule. Protons, electrons, dust, clouds, planets, people, anything that can, in principle, sit still, is forever kept below the light barrier. You can push something with mass faster and faster, but there's a twist. The closer you get to light's speed, the more energy you have to pour in for smaller and smaller gains. The object behaves as if it's getting heavier, more resistant to being pushed, its energy and its effective mass tied together. As you keep accelerating, the numbers don't just climb, they explode. To truly reach the speed of light, you'd need a supply of energy without limit. Not just a better rocket or a cleverer engine, but something infinite, something the universe never puts on the table. For anything built from matter, light speed isn't a goal to hit, it's a wall in the grain of reality itself. You can lean toward it, but you can't pass through. That's why, when stories dream about crossing the stars in a single lifetime, they almost always turn to ideas like wormholes and warp bubbles, tricks that bend space instead of simply racing through it faster. Within the ordinary rules of motion, the speed of light is the end of the road. You might wonder, though, if light is moving that quickly all around you, why you don't feel it sweeping past like a storm of invisible wind. If so much of the universe is bathed in it, why doesn't it roar? The quiet answer is that light doesn't interact with you the way air does. It doesn't shove your body or rattle your bones. It carries energy enough to warm your skin on a sunny day, to drive the chemistry of plants, to slowly push tiny grains of dust in the emptiness of space. But it doesn't need a medium to move through. It travels just as happily through a vacuum as it does through glass or air. Light does its work with a kind of stillness. It moves in straight lines in empty space unless gravity bends its path. There is no turbulence for it to stir up, no pressure wave for you to hear. The fastest thing we know arrives without a sound, without a shove, unnoticed, until it meets something that can catch it or turn it aside. It's also one of the oldest storytellers in existence. Faint microwaves washing quietly through the universe right now are the stretched and cooled remains of light from the universe's beginning, a glow called the cosmic microwave background. Those photons have been traveling for almost 14 billion years, drawn out and softened as space itself has expanded around them. They no longer shine in colors your eyes can see, but they're still here, still on the move, still carrying a memory of a time when everything was hotter and more tightly packed. So when we say light is fast, we're talking about more than a number. We're talking about reach and about patience. Every ray of light that reaches you has completed a journey, whether it began at a lamp across the room or at a star half a galaxy away. It ties now to some then, making this moment a small collage of different ages. The only reason we know anything at all about the wider universe is because light has brought us news late, sometimes outdated, but faithful. And still, the question doesn't quite let go. Is this really the ultimate, or just the fastest messenger that answers when we call? Most of the time, when we speak about speed, we imagine travel, a car driving from one town to another, a plane crossing an ocean, a signal moving through a cable. There's a starting point, an ending point, and a road in between. But what if not everything follows that pattern? What if some connections don't involve travel at all? Here, quantum physics leans in with a strange whisper. In the quantum world, two particles can be prepared in such a way that their properties are deeply linked. Separate them by a room, by a planet, by light years, and they still behave as parts of the same setup. Measure one, and you immediately know something about the other. This is quantum entanglement. It doesn't send a usable signal. You can't use it to flash a secret code faster than light. Almost everyone who studies it agrees on that. No cheating, no messages outrunning photons. Even so, entanglement asks a gentle question about what we mean by travel. If two things are connected in a way that doesn't seem to care about distance, they aren't sending anything from here to there. They're sharing a state that stretches across space. Light speed may remain the limit of motion, of signals sent through space, but perhaps there are kinds of relationships that don't live on that road at all. To get closer to an answer, we have to return to the fabric everything is woven into. Einstein's great insight was that space and time are not separate stages. They're different faces of one continuous thing, spacetime. It's not just a poetic image, it's the stage the universe performs on. In that framework, the speed of light isn't just a fast value we happen to measure. It's part of the stitching of the fabric itself, like the tension in a string or the steepness of a slope. You can imagine space-time as a kind of four-dimensional landscape with built-in rules for how paths can bend and how events can be ordered. In that landscape, the speed of light shows up as a fundamental tilt. The angle that divides what can influence what. Go slower than light, and your world has a certain structure. Try to go faster than light, and the geometry stops cooperating. Directions that were meant to be later and somewhere else begin to blur into each other, cause and effect lose their clean order. So, when we talk about light's speed as a limit, we're not just saying nothing can beat this in a race. We're saying this is how reality is shaped. If we ever did find something genuinely moving faster than light through space, no stretching of the map, no clever loophole, we wouldn't just be adding a new character to the story. We'd be discovering that the pages themselves are bound differently than we thought. We're not there. For now, we stay with what light is already telling us. It has no mass, no rest, no way to sit down. It doesn't carry a fuel tank. It doesn't need to be pushed. It doesn't get tired. And yet, it never goes any faster than that particular number, roughly 300,000 kilometers per second. Always, everywhere, the same. To understand why, we have to gently set aside the feeling that speed is something you can always increase if you just try harder. On familiar scales, that's often true. Press the gas pedal and the car goes faster. Give a runner more training and their pace improves. Add energy, get more speed. But near light's realm, the trade changes. In relativity, energy and mass are two sides of the same coin. The more energy you pour into an object to make it move faster, the more mass-like it behaves. It becomes harder to shove, more stubborn against acceleration. You're not just increasing its speed, you're deepening the way it weighs on space-time. Each new burst of energy buys you a smaller increase in velocity. As you approach the speed of light, the cost curves upward into something that mathematically never ends. Infinite energy for a finite mass to reach that last tiny step. Light stands apart because it never had to climb that hill. Photons don't start at rest and work their way up. They are born at full pace. Every photon that has ever been created from the early universe to the glow of your bedside lamp has moved at the same ultimate speed from the instant it came into being. You can bend its path with gravity or glass. You can absorb it and turn its energy into warmth. You can reflect it, sending it back the way it came. But you can't persuade it to slow down and stay. In that sense, light is the most reliable traveler we know. Wherever you go in the universe, however fast you yourself are moving, if you catch and measure a photon in empty space, you get the same answer for its speed. That consistency isn't just convenient, it's the foundation under much of what we do. Our clocks, our satellite navigation, the way we synchronize distant devices, all of it leans on the fact that light's pace does not drift. We trust it so deeply that we've flipped the way we define distance. Instead of asking, how fast does light move across a meter? We define a meter as the distance light crosses in a small, fixed fraction of a second. Space is measured by light's footsteps. If its speed were not constant, the rulers of our world would stop agreeing with each other. Technology built on timing would wobble. You can feel the same limit in more subtle ways. That boundary on speed means that influence cannot leap instantly from one place to another. You can't decide something here and have it physically change a distant star in the exact same moment. Even gravity, which feels immediate when you drop a pen or take a step, moves at the speed of light when it travels across empty space. When two black holes spiral together and collide, the ripples in spacetime, they create gravitational waves spread outward at that same top speed. We detect them long after the event itself is over. In a universe so large that delay means there is always more happening than any one place can be aware of. Countless collisions, quiet births of stars, quiet deaths of others are unfolding right now in regions whose light has not yet reached us and might not reach us for billions of years, if ever. Light is doing its careful, relentless best to keep us in touch, but even light has a schedule it cannot break. There is something tender in that realization. Every photon that arrives in your eye, every point of brightness on a sensor, is a traveler that has obeyed the same rule from start to finish. It has crossed the gap without resting, without getting lost, without changing its pace. It doesn't bring a message in words, but it brings proof that somewhere, something happened. A star burned, an atom jumped, a surface reflected. And somehow, across all that emptiness, that tiny event and your quiet moment have been joined. So when you wonder why light has a limit, you can think of it as more than a ceiling. It's also part of the rhythm that separates now from not yet, that divides what can be touched from what can only be witnessed, that shapes the size of our stories. The universe seems to need that rhythm, the time it takes for effects to follow causes, for news to arrive, for relationships to form and fade. Without it, the flow of events would lose its shape. When we talk about speed, in the simple way we learn as children, it all sounds straightforward. Distance divided by time, how far you go and how long it takes. But the more closely you look, the more speed turns out to be a relationship rather than a single number. To say something is moving is always to ask, moving compared to what? A car going 60 miles an hour is moving that fast relative to the road, but the road is spinning with Earth, and Earth is circling the sun, and the sun is looping around the center of the galaxy. There is no single, absolute speed. Everything, everywhere, is in motion relative to something else. There's no cosmic platform that counts as perfectly still. In that restless dance, the one pace that doesn't depend on your point of view is the speed of light. No matter where you stand, no matter how fast you're riding along with planets or stars, that number remains. In a universe without a universal rest frame, light's speed becomes the closest thing we have to a universal standard, a quiet, unwavering thread running through all the different perspectives, keeping the story stitched together. For almost everything in our lives, speed is a story told from a particular point of view. A car is fast compared to the road. A gust is quick compared to the leaves it stirs. Even something you call still is resting only relative to something else. Underneath that calm, it's riding Earth's spin, Earth's orbit. The suns drift through the galaxy, one layer of motion laid over another, a stack of change hiding beneath the feeling of rest. Against that shifting background, light's unchanging pace is what lets us compare, measure, and make sense of all those different motions without the story falling apart. At its simplest, speed is just change, a change of position over a change of time. But both of those words, position and time, are less solid than they seem. We like to picture space as a fixed grid we could draw, up and down, left and right, all neatly marked. We like to imagine time as a single, invisible clock that ticks the same way everywhere. Relativity says gently, not quite. Space can curve around mass and energy. Time can stretch or shrink depending on how fast you move or how strong gravity is. They're not separate, not absolute. They're two faces of a single fabric spacetime, and that fabric flexes. When something moves, it isn't gliding across a rigid stage. The stage itself is part of the motion. Within that fabric, light draws the sharpest path. If you think of space-time as a surface and every journey as a line across it, then light marks the steepest slope any influence can follow. Nothing with mass can tilt its path more steeply than that. Try to lean beyond the angle set by light, and you're not just going faster, you're asking space-time to do something it isn't built to do. Seen this way, the speed of light stops being a mere number and becomes a rule in the geometry of reality. It appears in equations far beyond optics because it is tied to cause and effect. Light's speed is the outer edge of causal contact, the maximum rate at which one event can influence another. If something could carry a signal faster than that, the order of before and after would begin to wobble. On a space-time diagram, faster-than-light paths lean so far they tip back toward the past. A message could arrive before it is sent. An alarm could sound before the danger exists. Cause and effect would tangle. As far as we can tell, the universe does not allow that. Every careful test we've made finds that influences stay inside the light-shaped boundary. The speed of light is less a suggestion and more a fence around what kinds of stories are possible. Away from diagrams, speed is something we feel. When a car rushes by, you don't see numbers floating above it. You notice the blur of its outline and the way its sound shifts pitch as it passes. That change, the Doppler effect, is your ear's reading motion as a change in frequency over time. Our senses are tuned to certain kinds of motion. If something moves very smoothly, like Earth orbiting the Sun, or the Sun circling the galaxy, we feel nothing at all. There is no jolt, no sway, no hint that we are racing through space. Without contrast, motion disappears. That invisibility makes the idea of anything faster than light even harder to grasp. How would we recognize it? The signals we trust, light, radio, any disturbance in a field, would all arrive late. We might see an effect without ever catching the thing that caused it. It would be like hearing distant thunder from a storm whose lightning never reaches your sky. You'd know something happened, but not what story led to it. In the quantum world, the notion of speed frays even more. Tiny particles do not usually carry sharp labels that say, "here," and "moving this fast." Until we interact with them, they live in a spread of possibilities, a haze rather than a dot. A measurement forces them to show up as here, with this much momentum. Between one measurement and the next, their path is more like a bundle of potential routes than a single curve. So down at that scale, a definite speed is almost meaningless. Speed becomes less about a neat track and more about probabilities unfolding in time, a reminder that our everyday language fits the quantum world only loosely. There is another angle. Speed is not only about how fast an object moves from A to B, it is about how quickly information can spread, how soon one place can learn that something has happened in another. When you push on one end of a long rod, the far end doesn't feel it instantly. The disturbance travels through the material at the speed of sound in that substance, carried by atoms nudging atoms. Different materials pass that shove along at different rates, but all of them stay within a broader limit. Light's speed sets the ultimate ceiling. Nothing that carries energy or information has ever been seen to jump over that limit. If something could, it would be like cutting ahead of the universe's own conversation. The answer would arrive before the question. Quantum entanglement tempts us with something stranger. Two particles can be prepared so that their properties are deeply linked, no matter how far apart they later drift. Measure one, and the statistics of the other adjust to match, as if they were two halves of the same quiet decision. From the outside, it looks like an instant connection across any distance. But no usable information is traveling in that instant step. You can't choose the outcome on one side to send a message to the other. The pattern only makes sense when you compare results afterward, and that comparison still has to obey light's limit. The universe keeps its boundary, even when its behavior looks spooky. Some physicists even wonder whether space-time itself might be a surface hiding something deeper, some web where distance and duration are not the basic ingredients. If an idea like that is ever confirmed, it could change what we mean by speed, not by breaking light's limit, but by shifting the level at which we ask the question. For now, though, the speeds we can talk about with confidence live inside space-time's fabric, measured against light's steady pace. Everything from a drifting leaf to a spacecraft is timed relative to that top speed. Light remains our benchmark and our ruler. And the more you think about speed, the more you find time sitting quietly at its heart. Without time, there is no per second, no way to say that one motion is quick and another slow. Near light's limit, that very flow of time depends on how you move. A fast traveler ages more slowly than someone who stays at home. Their own seconds feel normal, but from the outside, they are stretched. Close to the speed of light, the meaning of speed and the experience of time fold into one another. Not all swift things demand attention. Some pass through the world like a soft breath, a faint breeze that stirs a curtain and then is gone, a shadow sliding along a wall while you're looking somewhere else. Motion can be quiet. Not all speed is loud. Light is like that. For all its swiftness, it never makes a sound as it travels. It does not rattle the air or roar in your ears. It crosses the space between sun and earth and arrives without a whisper. You only know it is there when it is absorbed, reflected, scattered, when it warms your skin or brightens a room. Shadows remind us that movement can be deceptive. A shadow is not a thing in itself. It's an absence, a place light does not reach. When the object that blocks the light moves, the shadow seems to glide and stretch under the right conditions. That apparent motion can outrun light's own speed. A spotlight sweeping across a distant wall can make the edge of a shadow race from one end to the other, faster than any photon could cross that same distance. No law is broken, because nothing physical is actually traveling along the wall at that speed. Different photons are striking different points at different times. Your eyes stitch those events into the illusion of a single shape rushing by. The motion belongs to the pattern, not to a particular particle. The same is true if you sweep a laser pointer across the face of the moon. The dot might seem to skim across lunar craters faster than light could run, but there is no single dot skating over the surface. Each photon in the beam takes its own path to its own patch of dust. What you see is a moving highlight, a shifting endpoint where many journeys happen to land. This kind of motion, the kind that doesn't carry anything from here to there, is different from the motion that moves energy or sends a signal. It can look fast, but it doesn't change anything at that apparent speed. It doesn't push, it doesn't transmit information. It's more like color sliding across a screen as the pixels change, even though nothing is flowing across the glass. That difference matters. In physics, what really counts as speed, in the deep sense, is tied to influence. Can this process transfer energy? Can it send a message? Can it make a measurable change far away? If it can, then it is bound by light's limit. If it cannot, then any apparent, super-fast motion it shows is a kind of mirage, a trick of perspective and geometry. Shadows and sweeping beams may not let us cheat the cosmic speed limit, but they do give us practice separating what moves through the world from what only seems to. They help us draw a line between the physical and the perceptual, the real and the apparent. That line becomes even more important when we talk about space itself. Space is not just an empty container. It has properties. It can bend around mass, and it can stretch. It can ripple when a gravitational wave passes through. Born from events like black holes colliding, the distances between points in space grow and shrink in a gentle rhythm. The wave doesn't blow past like air. It moves everything together so subtly that you would never feel it. To notice it at all, we compare the lengths of laser beams bouncing between mirrors and long tunnels. When a wave arrives, those lengths change by a tiny amount. Motion, here, is not about objects sliding through space, but about space itself flexing. On the largest scales, the same idea appears as cosmic expansion. Galaxies are not simply flying apart through a fixed void. The void between them is growing. As space stretches, faraway galaxies recede from us in such a way that their apparent speeds can exceed light's without anything locally outrunning light. They are mostly following along with their nearby patch of space. It is the distance between patches that changes. Some galaxies are so far that, carried by this expansion, they are receding faster than light could ever close the gap. Any photon they send now will never reach us. All of this is a reminder that speed, in the broadest sense, is not always about simple motion from here to there. Sometimes it is about slow, steady change in the background, happening everywhere at once. A silent wind of expansion, a shiver of space-time, a ripple moving through the deep structure of reality. Even light, the fastest messenger we know, is part of that hush. The sun's rays cross empty space without a murmur. Only when they meet matter do they become warmth, or sight, or growth. The journey itself is silent. So the question, is speed always what it seems, lands softly. Maybe the speeds we notice are just the ones that intersect with our senses and our instruments. The universe may hold kinds of motion and connection that don't leave marks we currently know how to read, not because they defy the laws we've discovered, but because they move along paths we have not yet learned to trace. Physics answers that uncertainty by watching patiently. When we cannot see the cause, we look for the footprint. We search for small mismatches between prediction and reality, for shifts that say quietly, something is missing from your picture, not in the hope of catching a single particle sprinting past light's barrier. but in the hope of glimpsing new ways that change can flow. Through all of this, light still feels like it should go first. We use it to measure distance, to synchronize clocks, to define speed itself. It races ahead of slower messengers and sketches the outlines of distant things before anything else arrives. So it can be startling to realize that even light doesn't always move at its full pace. Its famous top speed, about 300,000 kilometers per second, belongs only to perfect emptiness. In a true vacuum, where nothing stands in its way, a photon moves at that ultimate pace. But most of the universe isn't empty at all. Slip light into air, or water, or glass, and its journey softens. It's nudged by electrons, scattered a little, guided and delayed as it threads its way through the crowded places. Seen from afar, it looks as though light itself has slowed. The cosmic limit still holds out in the quiet of a vacuum, but inside matter, even the swiftest messenger pauses for a breath before moving on. After all, when you flick on a flashlight in a dark room, nothing about it feels slowed or interrupted. The beam seems to bloom everywhere at once, touching the walls and ceiling as if it had already been waiting there. Sunlight pouring through a window feels the same, immediate, effortless, sudden. Our senses aren't delicate enough to notice the tiny hesitations that happen along the way, the small moments where light meets the world and adjusts its pace. But if you follow that beam down to the scale of atoms, the story changes. Light moving through a material doesn't simply glide like a ghost through an empty hall. It has to thread its way past a crowd of charged particles and fields. In water, the overall effect is that light travels at about 3/4 of its top speed. In glass, it slows even more. That gentle delay is what lets lenses bend and focus beams. The deeper picture is more subtle than little particles stopping and starting. It's a helpful cartoon to imagine a photon being absorbed by an atom and then re-emitted over and over. But reality is softer than that. Light, as both wave and particle, interacts with the electrons and electromagnetic fields inside the material in a collective way. The passing wave and the sea of atoms respond together, and that shared response determines how quickly the disturbance can move. From our point of view, the beam behaves as if it has slowed down. The front edge arrives a little later than it would in empty space. The photon is not tired or reluctant. It is simply obeying the rules of the environment it travels through. The medium shapes the path and quietly sets the pace. People have learned how to lean into that idea in remarkable ways. Using very cold gases and carefully tuned lasers, physicists have coaxed light into moving much more slowly than it does even in glass. Under the right conditions, a pulse of light can creep along at walking speed, just a few meters per second. In some experiments, the pattern of the light has been transferred into a cloud of atoms, held there for a moment, and then drawn back out again, like setting a note gently down and later picking it up. Nothing truly supernatural is happening. The light is not frozen like a photograph. Its information is stored in the atoms and then restored. The top speed in a vacuum, often written as c, remains untouched. That is the true ceiling. What changes is how difficult the surroundings make the journey. Once you notice that light can be delayed, another question slips in. If the path slows light down, can something else in that same path get ahead of it? In some situations, the answer is yes, but only in a very specific sense. Inside certain materials, charged particles can be pushed fast enough to outrun light's reduced speed in that medium, even though they never outrun light's vacuum speed. When that happens, the particle leaves behind a luminous wake, like the V-shaped ripple behind a fast boat on a lake. This glow has a name: Cherenkov radiation. You can see its faint, eerie blue in the water surrounding fuel rods inside some nuclear reactors. The water isn't mysteriously glowing on its own. What you're seeing is light's version of a sonic boom. The charged particles are moving faster than light can move through that water, and the disturbed electromagnetic field answers with a cone of light. Nothing in this scene breaks the deeper limit. In empty space, light still wins every race. But in that pool, for that brief moment, light is not leading. Another messenger has slipped past along a particular lane. The cosmos offers another quiet example. When a massive star collapses and explodes as a supernova, it doesn't send a single kind of signal. Along with light, it pours out a storm of neutrinos, tiny, almost weightless particles that rarely interact with anything. Neutrinos cross matter as if it were almost empty. Inside the dying star, light has a much harder time. It scatters off dense clouds of hot, tangled matter, bouncing around like someone trying to squeeze through a packed crowd. Neutrinos, nearly indifferent to the chaos, slip straight through and race outward. So by the time both messengers have crossed space and reached our detectors, the neutrinos can arrive first. That's what happened with a nearby supernova observed in 1987. For a brief, quiet moment, detectors on Earth caught a faint burst of neutrinos. Hours later, the light of the explosion finally reached our telescopes. They simply had fewer obstacles along the way. Even in laboratories, we've seen patterns that look, at first glance, as though they outrun light. In some experiments, pulses of light sent through special materials have peaks that seem to emerge from the far side earlier than they should, as if the pulse has somehow jumped ahead of itself. Physicists call these effects superluminal group velocities. The phrase sounds dramatic, but when you look closely, no actual information sneaks past the limit. The real signal, the part that carries anything truly new, still respects the boundary set by C. Cherenkov glows, early neutrinos, strange wave packets. All of these edge cases share something. They remind us that fastest depends on context. Light in a vacuum is still the ultimate messenger we know. But in crowded, dense, or carefully tuned environments, it can be slowed, blocked, or scattered, and when it hesitates, other players sometimes take its place as first arrival. So far, there is no solid evidence that any influence or message can exceed light's vacuum speed. Every careful experiment, every observation we trust, folds back onto the same quiet conclusion. The limit holds. Even so, the universe keeps showing us that the story around that limit is textured. Light might be the fastest, straightforward runner, but the path it takes can be full of detours and delays. There's a small comfort in that. Light, for all its brilliance, is not demanding. It does not insist on leading every parade. It moves as quickly as the road allows, sometimes racing, sometimes waiting, sometimes trapped and forced to find another way. Whenever it finally arrives after a footstep across a room or a journey of millions of years, it carries with it a piece of somewhere else, a record of a moment that has already passed. If there really is a speed limit written into the universe, and everything we know suggests there is, then there must also be places where that limit becomes a hard edge, places where even light's persistence cannot carry it through. Somewhere, the fastest thing we know reaches a line it cannot cross. One of those places wraps itself around what we call a black hole. A black hole is more than just a heavy object with strong gravity. It is a region where the fabric of space-time curves so sharply inward that paths which once led outward no longer do. Inside a certain boundary, the event horizon, every possible route forward in time, draws you deeper in, closer to the center. There is no path that climbs back to the wider universe. Light tries. A photon emitted just inside that boundary can aim outward with all its might and still never reach open space. The geometry is against it. It is like trying to climb a hill whose slope keeps steepening beneath your feet until up slowly turns into down. There is no monster grabbing the light and pulling it back. There is only the shape of space-time itself, funneling every future inward. From far away, this creates an odd illusion. If you could watch something fall toward a black hole and stay safe, you would never quite see it cross the horizon. Its signals would appear to slow, redden, and fade as it approached the edge. Time near the horizon would seem to stretch, each moment taking longer and longer to reach you. Eventually, the falling object would simply vanish from sight, frozen just above the boundary. From the traveler's own point of view, though, nothing special happens at that line. There is no bump, no shock, no visible gate. They cross the horizon without ceremony and continue inward, carried by the flow of space-time. Their time feels normal. It's only when you compare their experience to the outside universe that you see how differently the clocks are running. The speed limit on light, combined with extreme curvature, has created a one-way border between can send a message and cannot. That is what makes a black hole a true speed trap. It does not stop light by pushing against it. It traps light by redesigning the roads so that every direction leads in. Outside, light still moves at its usual top speed, but even that is no longer enough to bring information out from within. On the largest scales, the universe holds another boundary of a similar kind, gentler, but no less real. Light has had only a finite time to travel since the universe began. Because of that, there is a maximum distance from which light could possibly have reached us by now. And because space itself has been stretching as it goes, that distance is larger than a simple age-time speed calculation would suggest. Still, beyond a certain range, any light that starts toward us today will never arrive. The space in between is expanding too quickly. The signals are carried away, always a little too late. The edge of the region we can, in principle, see is called the observable universe. Everything inside that bubble is, at least in theory, connected to us by light. Everything beyond lies outside our reach, not because it is hidden behind a curtain, but because its messages will always be outpaced by expansion. Its light is forever on the far side of just-in-time. That, too, is a kind of horizon. No one drew it, but it is still a boundary set by timing. There may be galaxies beyond that edge, full of stars and perhaps planets, whose light will never touch our sky. Their stories are real, but they are not part of our view. Thinking about this changes the feel of the speed limit. It stops being only a line in an equation and becomes something more personal, an understanding that there are places and histories we will never visit or even see. Even if we built a ship that could travel at 99.99% of light speed, we would still be confined to a modest neighborhood compared with the whole. The rest would remain elsewhere, not by choice, but by design. There is a sadness in that, if you let it sink in, the idea that some separations are not just practical, but fundamental. No amount of effort can make a message outrun light or leap beyond certain horizons. Some parts of the universe will always be beyond our conversation, and yet, within the region where light can reach us, there is a deep, quiet grace. Every star you see, Every distant galaxy caught by a telescope is proof that light has bridged an enormous gap to arrive here. Photons from the early universe still bathe space in a faint background glow, carrying whispers from a time before there were stars at all. Light's speed, with all its limits, gives our view a rhythm. It means we discover things slowly. There is always more on the way, more signals in transit, more moments whose light has not yet arrived. One photon at a time, the universe reveals itself, never in a hurry, always keeping to its own steady pace. People imagine ways we might someday slip around these boundaries, tunnels through spacetime, sometimes called wormholes, or engines that warp the fabric so that distances shrink in front of a ship and stretch behind it. If anything like that is ever possible, it would not exactly break the speed limit. It would change what we mean by distance and duration, rewriting the road instead of making the traveler run faster. For now, those ideas live on the edge of our understanding, more dream than design. The speed of light in a vacuum still stands, quiet and firm, at the center of what we know, a limit, a guide, and a reminder that even the fastest stories in the universe are told one step at a time, bound to the shape of the fabric they move through. Somewhere, just beyond the border, drawn by light's speed, there is, at least in theory, a strange territory our instruments have never reached. On paper, it is inhabited by particles that don't fit comfortably in the world we know, figures that appear in equations rather than in detectors. They aren't required by what we've seen, only permitted by the mathematics. People call them tachyons, from a Greek word for swift, and even that feels like an understatement. If tachyons exist, they wouldn't merely be quick, their very nature would be to live forever, faster than light. They wouldn't sprint up to the speed limit and then push past it. They would never be on our side of the line at all. While every familiar particle with mass is trapped beneath light speed, straining toward it and never reaching, a tachyon would inhabit the opposite regime. It would always lie beyond the barrier, forever superluminal, like a traveler who can only walk on the far bank of a river we're not allowed to cross. Everything made of ordinary matter meets the usual resistance. The more energy you pour into it, the closer it creeps to light speed. But the harder each step becomes. Push toward the limit, and the energy you need curves toward infinity. Photons escape that trap because they have no rest mass at all. They don't start slow and work their way up. They are born at the limit, move at the limit, and vanish at the limit. That is simply where they live. Tachyons, if nature has chosen to include them, would be even stranger. In the language of relativity, their mass would not be small, but imaginary in the mathematical sense, tied to the square root of a negative number. Imaginary numbers appear all over physics as tools, ways to track phases, oscillations, and quantum states. We don't think of them as fake, just abstract. But when you plug an imaginary mass into the usual formulas for motion, something curious happens. The allowed speeds all lie above the speed of light. No solution at or below c makes sense. In that mirror world, adding energy slows the particle down toward the light barrier from above, and taking energy away makes it race even faster. Light speed becomes a floor it can never quite reach. On our side, nothing with mass can be pushed up through the barrier. On that side, nothing with imaginary mass could be pulled down through it. The boundary is shared, but each realm leans toward it from its own direction and never meets the other halfway. If such particles must always outrun light, how could we ever notice them? Our usual tools rely on interaction, particles knocking electrons loose, leaving tracks in gas, lighting up crystals, the faster and more ghost-like something is, the more easily it may pass through matter without leaving a mark. A truly superluminal visitor could slice through planets and stars and come out the other side almost unchanged. Even so, physicists are used to listening for absences and mismatches. If you can't see the culprit directly, perhaps you can see the outline it leaves in what remains. An imbalance in energy after a collision, decay products that don't quite add up, statistical bumps that refuse to disappear as the data grows. High-energy experiments have searched for signs like these that might hint at tachyon-like behavior. So far, nothing has settled into a clear, repeatable trace. In many modern theories, tachyons show up not as predictions of real particles, but as warnings that the state you're describing is unstable. If a field's lowest energy configuration seems to contain a tachyon, it usually means you've placed the system on top of a hill instead of in a valley. The equations can describe that position, but any tiny disturbance will send the system rolling toward a safer state. Once you let it settle into the valley, the apparent tachyon disappears from the description. It was never a promised particle, only a sign that your starting point wasn't truly at rest. And yet, the question lingers like a soft echo. What if something like this is real? What if, somewhere in the deep dark between galaxies, there are entities that drift so quickly we will never catch them slowing down enough to talk to us? Not because they refuse, but because their entire existence unfolds in a band of speed we can only point to from afar. It's an unsettling thought, and also a quiet one, like wondering whether there are currents in the deep ocean so swift that no ship will ever feel them. If you allow such things, another problem arrives with them. In Einstein's relativity, speed, space, and time are woven together. When you permit signals to travel faster than light, then in some frames of reference, those signals will appear to run backward in time. A message sent later from one place can be received earlier at another. Once you take into account different states of motion, you can draw diagrams in which two observers exchange superluminal signals, and each one receives the reply before sending the question. On paper, this is only geometry. Tilt a line steep enough on a space-time diagram, and it intersects slices of now in unusual ways. But to our sense of cause and effect, it feels like a knot. Could you send a warning to your own past? Could an effect quietly erase its own cause? Most physicists see that tangle and step back. They suspect that whatever the equations allow in principle, nature quietly forbids in practice, protecting causality behind the same speed limit that has survived every test so far. So tachyons stay where they began, as guests in the mathematics, not in the data. They are reminders that our equations can describe more possibilities than the universe actually uses. And even if nature never realized them, thinking about them clarifies why light's limit seems tied so closely to the order of events. Break the limit with a real signal, and you don't just go fast, you rearrange before and after. Tachyons are not the only ghosts wandering the edges of theory. Quantum physics is full of entities that hover between being and bookkeeping. Virtual particles, for example, show up when we calculate how other particles interact. They are short-lived ripples in fields, allowed to borrow energy as long as they return it quickly. We never see them directly in a detector, but their effects are real. Tiny shifts in energy levels, corrections that let theory and experiment line up with striking precision. Then there is dark matter, which is less a whisper in an equation and more a steady pressure on the cosmos itself. We cannot see it shine. We cannot hold a piece of it in our hands. Yet we watch galaxies spin too quickly to be held together by visible stars alone. We see clusters of galaxies bend light from even more distant objects in ways that require extra mass. Something unseen is shaping motion on the largest scales. Whatever it is, it reminds us that the most influential ingredients in the universe can also be the hardest to detect. Somewhere between these extremes lie ideas about new fields, new particles, new structures of space that might tug gently on mass or time in ways we haven't yet learned to measure. Their presence in our theories acts like a row of small flags along the border. Here is where your understanding thins. Here is where new questions begin. All of this prepares the ground for another kind of strangeness, one that doesn't ask anything to outrun light, but instead questions whether some connections need to move at all. There is a place in quantum theory where distance seems to soften, where two things can behave as if they are still one system, no matter how far they drift apart. They don't pass messages. They don't tug or pull across the gap. They simply share a description. This is quantum entanglement. When two particles become entangled, their properties spin, polarization, momentum are no longer independent. Instead of each having its own separate wave, they are described by a single joint wave function. You can't fully talk about one without also talking about the other. Before you measure them, neither has a definite value for the entangled property. Each is in a superposition of possibilities with only one firm rule. The outcomes must match the shared pattern. If the total spin of the pair has to add up to zero, then whenever one is found up, the other must be down. But those directions aren't secretly carved into the particles from the beginning, at least not in any way that fits the experiments we've done. Until you perform a measurement, the pair lives in a blended state of up-down and down-up at once. The strangeness shows itself when you separate the particles and finally look. You measure one, and in that moment, its state becomes definite. Instantly, the other's state becomes definite too, in a way that perfectly complements the first. You don't wait for a light speed signal to cross the distance. The statistics make it look as though the universe coordinated the outcomes in a single move. Einstein disliked this. He suspected there must be hidden variables, unseen instructions carried by the particles that determine the results in advance, making the whole instant connection an illusion. For a long time, that was a reasonable hope. Then John Bell came along, and with him a series of experiments that tested whether such hidden instructions could exist. The answer, repeated many times in many ways, was no. The world violates the bounds any local hidden variable theory would require. Quantum entanglement is real. Even so, it doesn't let us send messages faster than light. Each individual result is still random. You can't choose how your particle will collapse when you measure it, so you can't encode a message in the outcome. Only when you later compare your notes with someone far away, a process that still needs ordinary, slower-than-light communication, do the strange correlations emerge. Causality survives. No paradox, no way to nudge the past. What entanglement gives us instead is a different lesson. Not all connection looks like a signal traveling from place to place. Some connections are built into the way a system is put together from the start. They emerge when you look closely enough, regardless of how wide the gap has grown. Some physicists think this might be more than a curious feature. They suspect entanglement could be part of the scaffolding from which space-time itself is woven. In some modern ideas, the geometry of the universe, the sense of here and there, of distances and directions rises out of vast networks of quantum correlations. The threads that bind the fabric might not be bits of space at all, but patterns of relationship. If something like that is true, even in outline, then our usual way of thinking about faster than light begins to feel narrow. Speed assumes a path laid out in advance, a traveler crossing that path, a clock timing the journey. Entanglement hints that some forms of togetherness don't use paths at all. They don't cross space, they help define it. In that view, the ultimate limit on speed remains in place for anything that carries energy or information along a route. Light still draws the fastest permissible lines through spacetime. Tachyon-like dreams remain, for now, only mathematical shadows. But in the background, there is a quieter suggestion that the deepest connections in the universe may not be about racing from here to there, but about a kind of built-in harmony, a shared structure that simply exists and waits to be noticed. We don't yet know how far that idea goes. For now, we sit with this layered picture, light tracing the edges of what can be signaled, hypothetical particles haunting the far side of the limit, and entangled systems reminding us that sometimes the most profound bonds don't travel at any speed at all, they just are, tying distant points of the universe into a single, softly humming whole. We tend to picture space as something calm and still, a dark stage where stars cross and galaxies drift, while the backdrop never changes. But the backdrop is not still at all. The stage itself is stretching, not as a blast racing outward from a center, not as something expanding into a bigger nothing, but as a quiet widening that happens everywhere at once, in every direction. The surprising part is how fast that widening can be. On the largest scales, the expansion of space can outpace even light. That doesn't mean whole galaxies are firing themselves like bullets through the void faster than any photon. It means the emptiness between them is stretching so quickly that the total distance grows faster than light could ever cross. When you look out into the night, you are always looking both far away and long ago. The farther your gaze reaches, the older the light has to be, simply because it had to travel so long to get here. At some distances, that travel is possible. At others, something changes. The fabric in between is swelling too quickly. Adding new length faster than light can make progress. No matter how patient you are, some photons will never arrive. They are forever caught on a road that is lengthening under them faster than their own steady pace. That moving boundary between can reach us and can't has a name: the cosmic horizon. Everything beyond it is receding from us, not by its own engines firing, but because the space between is expanding so fast that the separation grows at a superluminal rate. Like dots painted on a balloon as you blow it up, distant galaxies are carried apart without ever sliding across the surface. Relativity is fine with this. The rule that nothing can move faster than light applies to objects traveling through spacetime, not to the size of spacetime itself as it changes. General relativity, the theory that describes how gravity curves and shapes this fabric, allows solutions where the distances between far apart points grow faster than light, could race across them, and those solutions match what we see. The consequence is a little sobering. There are galaxies whose light will never grace our telescopes. They may have sent out photons billions of years ago, but while those photons were on their way, the stretch of space between kept expanding. The gap they needed to cross grew faster than they could close it. From our point of view, they are running on a treadmill that speeds up just enough that they never get any closer. Even some galaxies we can just barely see today will, in the deep future, drift out beyond our reach. Not because they flicker out or slam on rockets and flee, but because their light will be stretched thinner and thinner to longer wavelengths until it slips beyond what our instruments can catch. As expansion continues, their signals fade into a red so deep it is effectively silence. If the acceleration we've measured keeps going, there will come a far-off time when only a small island of the universe remains visible from here. Our local group of galaxies, bound together strongly enough to resist the pull of expansion. To any astronomer living in that age, the sky will look strangely empty. They may conclude that the universe is small and quiet, unaware that beyond their horizon lies an ocean of structures they simply cannot see. So faster-than-light expansion is not just a curiosity, it sets a limit on knowledge. It draws a line between the parts of the universe that can ever exchange light with us and the parts that will always remain reachless. The boundary is not a wall you can touch. It's made of time and distance together. And yet, within that limit, light still works its quiet miracles. Photons that began their journey when the universe was very young are still arriving now, washed into microwave wavelengths by billions of years of expansion. They form the cosmic microwave background, a faint, almost uniform glow that fills space. Hidden in its tiny ripples is a snapshot of what the cosmos looked like when it was only a few 100,000 years old. In that sense, even as expansion outruns light in some directions, light outruns forgetting. It keeps a record. It brings us news from epochs that no longer exist, giving us a brief window into moments that would otherwise be lost behind the moving horizon. We've also learned that this expansion is not steady. In the early universe, gravity from matter tried to slow it down, pulling everything inward. Later, something else began to dominate, a mysterious component we call dark energy, which seems to act like a gentle, persistent push built into space itself. Dark energy doesn't clump. It doesn't form stars or planets. It simply urges the fabric to stretch a little more and a little faster everywhere. Right now, that push wins. The expansion is accelerating. That means the cosmic horizon is effectively shrinking in what it reveals. More and more distant regions are being carried beyond the range from which light can ever reach us. Each passing epoch, fewer galaxies share a future in which we can see one another, even in principle. It's a strange feeling to realize that our universe holds limits not only of speed, but of reachable story. There are pages we'll never read, not because we lack the technology, but because no signal can ever bridge the growing gulf. Still, inside the pages we do have, the story is rich, stitched together by photons that have traveled across staggering distances just to lay their histories at our feet. Once you accept that space can stretch, another possibility comes into view. If it can stretch, it can bend. If it can bend, perhaps, in theory, it can fold. That is the idea behind wormholes, not so much tunnels dug through space as bridges where space-time is curved so that two distant regions touch. A simple picture lives on a scrap of paper. Draw two dots far apart and imagine a tiny creature that can only walk along the surface. To reach from one to the other, it must cross the whole distance. Now, fold the paper so the dots meet. For you, in a higher dimension, the 2 points are suddenly neighbors. The path between them has shrunk to almost nothing, even though, along the old flat surface, they were still far apart. A wormhole is the space-time version of that fold. a hypothetical passage that connects two mouths separated in ordinary space with a hidden throat threading between them. It might, in principle, link distant regions of our universe, or even different universes altogether, depending on how the geometry behaves. Einstein's equations admit solutions that look like this. One of the earliest, known as the Einstein-Rosen bridge, arises naturally when you write down the idealized description of a black hole. The catch is that most of these bridges seem to slam shut almost as soon as they form. The tunnel pinches off too quickly for light, let alone a traveler, to cross from one end to the other. Gravity pulls the throat closed with such force that the shortcut becomes useless. To hold a wormhole open, the equations whisper that you would need something exotic, matter with negative energy density, a form of stuff that pushes space outward instead of pulling it in. Such matter would fall uphill in a gravitational field. It would act like a kind of anti-weight, resisting collapse. In our everyday world, there is nothing like that. But quantum theory hints that, in certain configurations, tiny pockets of negative energy can flicker into existence for very short times, woven into the jittering vacuum itself. Those flickers are far too small and fleeting to prop open a usable tunnel. But they keep the door cracked. Conceptually, they say, this isn't completely forbidden, it's just extremely difficult. So people ask a quiet, what if? What if, in some far future, or somewhere in the wild reaches of the cosmos, larger scale effects could be coaxed into being? What if a wormhole could be stabilized, not forever, but long enough? If such a bridge existed and you could pass through, what would it do to the idea of speed? Locally, nothing would violate the light limit. Inside the tunnel, light would still be as fast as anything can go. But the distance it has to cover might be drastically shorter than the route outside. From the point of view of someone watching from afar, an object entering one mouth and exiting the other could appear to have crossed an immense span in less time than light would need to go the long way around. It would look like faster than light travel, but the trick would belong to geometry, not to the traveler. You would not have broken the speed limit. You would have taken a path light itself cannot use from the outside. As always, new paths come with new questions. Could a wormhole remain stable against tiny disturbances? Would the mouths drift relative to one another? Could such a structure be used to send signals as well as travelers? And, maybe most unsettling, what happens if one mouth experiences time differently than the other? General relativity suggests that if you move one end of a wormhole in certain ways, accelerating it or placing it near strong gravity, you could create a time offset between the mouths. In that case, stepping through might not only move you across space, but also into the past or future relative to where you began. The equations admit this possibility, at least in idealized scenarios. Whether the real universe quietly forbids it through instabilities we don't yet understand is an open question. For now, wormholes live in a borderland between allowed on paper and unseen in practice, like elaborate dreams stitched from serious math. Related ideas play with the same theme. If you can't make the traveler outrun light, perhaps you can make space itself carry them. The Alcubierre drive, a speculative concept from the 1990 seconds, imagines a spacecraft sitting inside a bubble of warped space-time. In front of the bubble, space would contract. Behind it, space would expand. The ship itself would barely move inside the bubble, but the bubble would surf along the wave of distortion. From the outside, the distance between departure and arrival could shrink so fast that the ship appears to have traveled faster than light would through flat space. Inside, no local law is broken. Light still rules the roost. But once again, the price tag is enormous. Vast amounts of exotic, negative energy would be needed to shape space this way, far beyond anything we know how to create or control. These ideas may never leave the realm of theory, and that's okay. They are valuable because they show us that speed is not always the only lever. In a universe where the fabric is flexible, changing the shape of the path can matter as much as how hard you push along it. Sometimes the shortest journey is not the one where you run the fastest, but the one where the ground quietly rearranges itself under your feet. All of this brings us back to something softer: the motion of information. Information is not a substance you can hold, but it behaves as if it has its own laws. You can encode it, erase it, scramble it, and move it from place to place, but you can't perfectly copy every quantum detail, and you can't make it vanish without a trace. And as far as we know, you cannot make it outrun light. Whenever something changes, a star flaring, an atom flipping its state, a door opening in a dark room, what matters to us is not only that it happened, but when we find out, the news of the event has to travel. That news might ride on a photon, or a radio wave, or a vibration in matter, but in every case it is ultimately limited by the same universal pace. Light is not just brightness. It is the carrier of meaning, the courier that lets distant events join our story at all. Everything we know about a distant star, a violent supernova, or a faint galaxy at the edge of our vision reaches us the same way, as light, or as signals that depend on light's pace in one form or another. Even in deep underground detectors where no human eye ever looks directly, the instruments are still listening for tiny flashes, for electrical pulses, for ripples that move at or below that same cosmic limit. Our picture of the universe is painted with photons and with messengers that keep to their speed. So what happens if we strip everything down and ask about information itself? Not the particles, not the waves, just the something happened that they carry. Could that, in some secret way, travel faster than light? Most roads lead back to no. Even the most delicate signal still needs a carrier, some physical change, some field or particle that can move from here to there. A whisper across a room rides on air. A radio call rides on electromagnetic waves. A command inside a computer rides on electrons and fields. However subtle the signal, something has to move, and as far as we can tell, nothing that can bear information outruns light in empty space. Not neutrinos, not gravity, not the trembling of quantum fields themselves. And yet, the universe keeps offering edge cases that make the question harder to let go. Quantum entanglement is one of them. When two particles are entangled, measuring one seems to fix the state of the other instantly, no matter how far apart they are. It feels, at first blush, like information, a kind of knowledge shared across distance, untouched by delay. But if you lean in, the story softens. You cannot choose the outcome of your measurement. You cannot decide, I will get this result, and use that choice as a code. The result arrives as a kind of cosmic coin flip, only when you compare your list of flips with someone far away, using ordinary signals that respect the speed limit, do the strange correlations reveal themselves. The instant connection shapes the pattern of outcomes, but it does not carry a controllable message from one side to the other. So entanglement does not quite let information outrun light. Instead, it nudges us to ask what we mean by information in the first place? Is it only a pattern we recognize after the fact when we compare notes? Or is it something more structural, woven into the way reality itself keeps track of possibilities and outcomes? There are other curiosities. In some cleverly prepared materials, the shape of a wave, a pulse of light, or another signal can appear to move faster than light would in a vacuum. The peak of the pulse seems to leap ahead, exiting a region before the main body of the wave has arrived. This is called a superluminal group velocity, and it's deeply counterintuitive until you look at the details. The key is that the part of the wave that truly carries new information, the front edge, where something changes from nothing to something, still travels at or below the speed of light. The rest of the pulse can be reshaped, compressed, or stretched by the medium so that its peak wanders forward, like a crowd shifting its center while each person moves modestly. No usable message gets to the other side faster than c. The apparent speed is a mirage made of interference, not a real shortcut. Hypothetical particles like tachyons tempt us in another way. If they existed, and if they could be tamed, you might imagine encoding bits into them and sending messages that beat every photon to its destination. But as we've wandered through, tachyons themselves remain unconfirmed, and the moment you try to harness them for signaling, the old problems of causality return. Signals that outrun light can be arranged in some frames of reference to arrive before they are sent. Entire conversations could loop back into their own beginnings. Logic starts to unwind. That's the deeper role of light's limit. It doesn't just manage traffic in space. It keeps time's arrow pointed in one direction. Cause first, effect after. Heat flowing from hot to cold. Memories pointing backward, not forward. The equations that describe motion, fields, and entropy all quietly assume that there is no influence coming from the future into the past. If we allowed reliable, controllable superluminal communication, that assumption would crack. The story of the universe could no longer be told as a sequence that unfolds. It would not itself. So for now, every solid test we know how to do gives the same gentle answer. Information cannot beat light and stay faithful to causality. That does not make the question a waste. Wondering about it pushes us toward a subtler picture in which information is not just what moves, but what is conserved. Black holes make that question unavoidable. When something falls into a black hole, a star, a cloud of gas, a lonely photon, it seems, from the outside, to disappear. Its properties, its detailed arrangement, the data that once described it, all vanish behind the event horizon. If information could truly be destroyed this way, it would violate a core principle of quantum mechanics, that, at the most fundamental level, information is never lost, only shuffled and scrambled. To patch this conflict, physicists have explored a variety of ideas. One is that the information is somehow stored on the event horizon itself, encoded in microscopic degrees of freedom on that two-dimensional surface. Another is that as black holes slowly evaporate through Hawking radiation particles leaking out over vast spans of time, the radiation is not completely random. Hidden in its subtle correlations could be the information that once seemed lost, dribbled back into the universe in a form almost impossible to recognize. These thoughts led to something even more radical, the holographic principle. It suggests, in rough terms, that everything happening inside a volume of space may be describable by information living on its boundary, much like a three-dimensional scene can be encoded on a two-dimensional hologram. In such a picture, information is less like a package traveling around and more like a bookkeeping rule, that the universe never breaks. Seen that way, the question, can information move faster than light, starts to tilt. Maybe information doesn't move the way a car does, or a photon does. Maybe it is the pattern that all these movements must respect, a framework underlying events rather than a passenger riding on top. The speed limit then belongs to the processes that reveal information to us, the emissions, interactions, and measurements that let one part of reality know what happened in another. The boundary remains, but its meaning shifts a bit. The speed of light doesn't just bound how fast things go, it bounds how quickly awareness can spread, how quickly knowledge can become shared. It sets the tempo at which understanding can propagate from one place to another. In that sense, asking whether information can outrun light is a way of asking whether we are allowed to know something before anything in the world has had time to be changed by it. So far, the universe answers no. No messages from the future, no effects before causes, no whispers that arrive before the event they describe has had time to happen. It is not a stern, angry, no, just the quiet consistency of a cosmos that values coherence over shortcuts. If anything ever did move faster than light, in the ordinary sense, it would slip out of the net our senses and instruments cast. You would never see it approaching. The light announcing its arrival would lag behind. You wouldn't hear it either. Sound, being slower still, would be even more delayed. By the time any signal reached you, whatever had passed would already be gone. Superluminal motion would be not only quick, but fundamentally out of sync with our ways of noticing. In the world we inhabit, speed usually comes with a kind of loudness. A jet tears the air and leaves a shockwave trailing. A train shakes the rails and the ground. Even a fast thought feels sharp, its edges bright in the mind. We associate quickness with impact and noise, with things that demand attention as they rush by. But any motion that truly slipped past light's limit would not behave like that. It would not push air because it wouldn't linger long enough. It wouldn't glow for us because the glow would fall behind. It would live, from our perspective, in silence. Not because it is mystical or specially hidden, but because it would leave no immediate trace in the channels we rely on. Light, sound, touch, delayed fields, brushing our detectors. Even the concept feels slippery. Every sense we own, every device we build, is tuned to signals that stay within or beneath light's constraint. The moment you imagine something that consistently moves faster, the scaffolding of measurement loses its grip. You cannot photograph what arrives before its own image. You cannot listen for a sound that cannot catch up to its source. You cannot reach to touch what never slows down enough to interact. In that way, superluminal motion, if it has any foothold in reality at all, belongs to a realm that is naturally disconnected from us. It would not simply be fast, it would be unreachable. Perhaps that is why it remains mostly a tool for thought experiments and stories. It lies outside the loop where action and observation can meet. And yet, even here, where our tools begin to fail, physics finds a way to listen for echoes. Sometimes, the most telling clue is not a signal, but its absence. Not a pattern we see, but one we expected and did not find. We can look for footprints in the snow even if we never saw the traveler. We can map limits by noticing where nothing happens. So when we talk about the silence of anything beyond light speed, we are also talking about the contour of our own reach. The speed of light becomes more than a constant in an equation. It is the line between what can join our story and what, if it exists, will always pass by without saying a word. Within that line, light keeps time. It sets the rhythm at which the universe can reveal itself, one signal after another, always arriving just late enough to remind us that knowing and happening are never quite the same moment. Even when we observe something as basic as a chemical reaction, what we're seeing is already old by the time it reaches our awareness. Bonds have broken and reformed. Electrons have shifted. Tiny packets of light have been absorbed and re-emitted. The story finishes at the atomic level, long before your eyes or instruments catch the starting line. Your brain receives only the echo, stitched together into a smooth experience. On some scales, the universe is quicker than we can truly follow. On others, it is slower than we can comfortably imagine. Somewhere between those extremes, we build our sense of fast and slow, of late and on time. Light happens to sit right at the edge of what's possible, a kind of maximum pace for how quickly one event can nudge another across empty space. But our lives unfold far below that limit, in a band where waiting and rushing are mostly human inventions. When you think about it that way, the question, is there anything faster than light, begins to soften a little. Light's speed is certainly a hard boundary for signals, for causes and effects that have to cross distances. Nothing with mass, nothing that carries information, gets to skip that line. But beyond the math, there's another question, sitting quietly underneath. Why are we so drawn to the idea of something faster? Part of it is simple curiosity. We like edges. Wherever there is a limit, we want to peer over it, to see what might lie beyond. Another part is our own restlessness. In our daily world, speed often feels like control. If we could move messages instantly from star to star, if we could cross the galaxy in a moment, it feels as though we would have conquered distance itself. The universe would become smaller, friendlier, more like a neighborhood, and less like an ocean. Yet the very delay built into light's journey is also what creates the beauty we keep coming back to. If starlight arrived instantly, the sky would no longer be a time machine. You would lose the quiet thrill of knowing that the light in your eyes tonight began its trip long before you were born, perhaps before humans existed at all. The finite speed of light stretches your gaze backward in time, turning every glance upward into a kind of gentle archaeology. Because of that delay, you can stand in the present and see the afterglow of the early universe, the broken shells of exploded stars, the ghostly arcs of galaxies whose shapes have already changed. The same limit that frustrates science fiction also gives you perspective, reminding you that now is a thin layer laid across a deep history of light, still on its way. There's another layer to this. The speed of light is universal, but the experience of time is not. A clock moving quickly, or sitting deep in a gravitational well, ticks more slowly than one at rest on your desk. To the clock, nothing seems wrong. Its seconds feel normal. But compared to a clock farther from gravity, or moving more gently, it lags. In that sense, speed changes not only how quickly you move through space, but how quickly you move through time. If you could spend your life traveling close to light speed and then return home, you would find that more time has passed here than in your own experience. Years, decades, maybe centuries, depending on how extreme your journey was. This is not a thought experiment anymore. It is a measurable effect. We see tiny versions of it in particles accelerated in labs, in satellites that need relativistic corrections to keep our navigation systems accurate. Light again sits at a kind of extreme in this picture. From a photon's point of view, if it could have one, no time passes at all between its creation and its absorption. Its entire existence is compressed into a single instant. However long the journey looks to us, it is born and it arrives in the same breathless moment. That's another way of saying that as you approach light speed, your own sense of duration begins to flatten, while the world you leave behind drifts ahead. So the universe doesn't just have a speed limit, it has a tapestry in which speed and time are woven together. Try to pull one thread faster, and the others shift in response. That's why faster than light isn't just about going quickly. It's about stepping outside the pattern that keeps events ordered, that lets stories unfold from cause to effect. If something could really move faster than light in the sense of carrying information, it would poke holes in that tapestry. You could, in principle, arrange things so that messages arrived before they were sent, so that warnings went backward along the timeline, so that closed loops of cause and effect formed with no clear beginning. Time would still exist, but it would lose its direction. Past and future would mix in ways our current physics simply doesn't allow. Maybe that's why, so far, every solid test we've made lines up with the idea that nothing usable outruns light. The universe seems to guard causality carefully, not with a visible wall, but with quiet consistency. Every time we look for a loophole, tachyons, sneaky signals hidden in entanglement, strange waveforms in exotic materials, the details fall back into line. Patterns may appear to move faster, apparent positions can jump, but the actual flow of information, the stuff of this happened and now that, stays inside the limit. That doesn't mean our questions are wasted. It just means that the answers are subtler than we hoped. Sometimes, when you push against the edges of a rule, you don't break it, you learn why it matters. In that light, the story we've been following becomes less about chasing a faster speed and more about understanding the roles speed already plays. Light carries images, warmth, and chemistry. It sets the pace for communication. It defines the structure of space-time. It provides the scale of the cosmos we can see. Dark stretches between stars are not empty of meaning. They are simply regions where the messenger hasn't arrived yet, or where its whispers are too faint for us to hear. Even darkness, in its shifting way, tells us something about motion and change. A shadow sliding up a wall, the night line sweeping across a planet, the dimming of a star as a planet crosses in front. All of these are patterns drawn not by a substance called darkness, but by light being interrupted. The absence has shape, and from that shape we infer the presence of things we cannot see directly. If you think of your own life like that, there's a kind of comfort in it. So much of what matters doesn't happen at the fastest possible rate. Friendships deepen over years, skills develop over practice. Healing, emotional or physical, rarely rushes. The universe itself, with its limited speed of light and its stretched-out timelines, seems to lean toward processes that take the time they need. When you look at the night sky, you are not seeing the universe as it is in this instant. You are seeing a layered collage of times, each distance mapped to a different age. Some of the stars in your view have already changed or died. Some of the galaxies have drifted further apart, but their light is still on the way, still making the journey, still offering you a chance to know that they were. Nothing in that picture has to outrun light to be profound. The power lies in the fact that light arrives at all, and that its finite speed lets you read history off the sky. The question, is there something faster, fades a little against the broader realization that speed is only one way to measure movement through reality. Direction, connection, and meaning matter just as much. Quantum entanglement hints that some forms of connection don't need to travel, they simply exist across distance. Cosmic expansion shows that space itself can change the rules for how far signals can go. Wormholes and warp bubbles, even as speculative ideas, remind us that reshaping the path can rival racing along it. In all of these, the focus shifts from how fast to in what way and at what cost. Maybe, in the end, the universe doesn't need anything faster than light, because it already has other ways of being whole. Entanglement knits distant particles into shared states. Gravity molds space-time into structures that hold for billions of years. Dark matter and dark energy influence the fate of galaxies without ever shining. Light, faithful and finite, weaves through all of it, carrying news at the only pace reality seems willing to share. Where does that leave us? In a small, luminous corner, moving slowly compared to light, quickly compared to mountains, wondering how it all fits together. We build detectors to catch rare particles, telescopes to catch old photons, equations to catch patterns in the data. We imagine tachyons and wormholes and universes stacked like pages in an invisible book, not because we are dissatisfied with the laws we know, but because curiosity itself has no speed limit. As you listen to these ideas, you don't have to decide what's true right away. Physics will keep doing its quiet work, testing, refining, adjusting. For now, it's enough to sit with the thought that fastest may not be the most important part of the story. The speed of light is a limit, yes, but it's also an invitation, a reminder that understanding takes time, that signals must travel, that perspective is built slowly out of what finally arrives. Right now, somewhere overhead, photons are on their way from stars you'll never learn the names of, slipping through interstellar dust, threading around unseen clouds of dark matter, obeying the same simple rule they have always obeyed. They will reach someone's eyes, or some sensor, or perhaps no one at all. Whether or not anything is faster than them, they are enough to light a sky, to draw a map, to whisper across impossible distances that the universe is there. You can think of it the way you might think of listening to a long, slow piece of music. You could imagine a version played at 10 times the speed, every note compressed into a blur, the whole thing over almost before it begins. It would be faster, technically, but something essential would be missing: the rise and fall, the feeling of where you've been and where you're going. The pauses between notes are part of the song. The universe has its own tempo. Light's limit is woven into that tempo, the way a tempo marking is written into a score. It tells you how quickly one part of the cosmos can learn about another, how long it takes for cause to echo as effect. It does not stop you from playing. It shapes the melody you get to hear. If someday we discover that there truly is some phenomenon that outpaces light in a deep, physical way, not just in appearance, not just in geometry, but in the real transfer of influence, our understanding of time and causality will have to grow to match it. We will need new language, new diagrams, new intuitions. But whatever we find, it will still have to sit gently with everything we already know works so well. GPS satellites, particle accelerators, the colors of sunsets, the quiet success of countless experiments that all rely on light behaving exactly as expected. Until that day, we live in a cosmos where the fastest messenger we trust is still light, and where even that speed leaves room for patience. The gaps between happened and known, between sent and received, are not flaws. They are spaces where perspective can form, where we can notice that distance exists at all, where we can feel, however faintly, the vastness between ourselves and the things we study. So when your mind circles back to the question that began all of this, is there a speed faster than light we just can't see? You can answer in two ways at once. In the strict physical sense, as far as any measurement has ever shown, no. Nothing that carries energy or information outruns a photon in a vacuum. Light's pace remains the ceiling, and reality seems to respect it. In another, gentler sense, there are forms of connection and change that don't fit neatly into that race at all. Entanglement doesn't travel, it simply is. Space doesn't move like an object, but it can stretch in ways that carry things apart faster than light could run. Shadows and patterns can appear to slide faster than any signal without actually moving anything. Relationship, structure, and geometry sometimes matter more than raw speed. Both answers can be true at the same time. The first keeps our theories grounded. The second keeps our imagination open. Between them, there is room for wonder, without needing to break the rules for curiosity that doesn't depend on loopholes. And in the quiet of the night, when the practical questions soften, and you are left with the feeling of being very small beneath a very large sky, the details of whether anything is faster than light may not matter as much as the simple fact that light, finite and faithful, is already on its way to you from places far beyond your reach. Those photons will arrive when they arrive, no sooner, no later. Each one a tiny, precise answer to a journey it did not choose, but always completes. You don't have to chase them. You just have to let your eyes or your thoughts be there when they finally cross the last small distance and fall quietly into your awareness. The structure of reality doesn't care about speed the way we do. It cares about consistency, about connection, about balance. When something happens in one place and its influence eventually reaches another, the universe only insists that the path fits the rules it has already written. That energy is conserved. That information is preserved. That cause has space to become effect. How long that takes is almost incidental. The clock is ours, not its. From that perspective, light's role becomes easier to see. It isn't a race winner showing off at the edge of possibility. It's a standard, a quiet metronome built into the fabric of spacetime. It sets the beat at which influence can spread, at which news from one corner can arrive in another. We can't ask for a faster tempo without changing the entire piece. If you tried to double the speed of light, you wouldn't just get quicker signals. You'd alter the structure of atoms, the way stars shine, the way matter holds together. What looks like a simple number in an equation is actually woven through everything. The urge to ask whether there is something faster is understandable. It's like wondering if there's a shortcut through the pages of reality, a way to skip ahead in the story. If we could jump without waiting, we think, we might touch distant galaxies, talk to whatever might live under other suns, see the universe in real time instead of in delayed replay. A kind of cosmic impatience quietly hides in the question. But when you step back into the calm of the night, when you remember how much of what you see comes to you only because it took so long to arrive, the question changes. Maybe the point was never to be live with the whole universe at once. Maybe the delay is part of what makes the view bearable, comprehensible, gentle. If every event everywhere arrived in your awareness exactly as it happened, it would be noise beyond imagining a simultaneous storm of beginnings and endings with no way to sort or breathe. Instead, the universe gives you layers. Nearby events arrive almost in step with you. The moon, sends light that is just over a second old. The sun sends light that is minutes old. Bright, close stars offer light that has been traveling for years. Distant galaxies send you scenes from billions of years ago. Your sky is not a single moment. It is a stack of moments, arranged by distance into a kind of natural timeline. The speed of light, by being finite, organizes the chaos into something you can actually hold in your mind. In that sense, our slowness isn't a flaw, it's a filter. We don't experience everything. We experience enough to notice patterns, enough to ask questions, enough to be surprised without being overwhelmed. Our senses would never pass for precision instruments in a lab, but they are beautifully tuned for a certain pace, a certain scale, a certain layer of reality, where trees grow, rivers flow, clouds gather and drift. The physics that rules black holes and cosmic inflation can feel alien from here, but it still threads through this ordinary layer in quiet ways. If you think about your own day, there's a mini version of all this. Messages take time to move between people. A word spoken enters the air, travels, reaches an ear, is translated into meaning, perhaps triggers a response. Even with digital tools, there are delays, tiny but present. A text leaves one device, bounces between servers, arrives at another. A reply forms, is typed, is sent. None of this is instant, even when it feels like it. And in those small delays, choices slip in. You decide how to answer. You decide whether to answer. You have time to soften a reaction, to think twice, to understand. If every thought leapt directly into action, if every impulse moved as quickly as light, our inner lives would be chaotic. The gap between feeling and doing, between noticing and reacting, is part of how we stay coherent. It's our personal version of the universe's insistence that things take time. On cosmic scales, that gap is measured in years, centuries, ages. On human scales, it's measured in heartbeats and breaths, in pauses between sentences, in the time it takes to fall asleep or to realize that the night sky is making you feel something you can't quite name. But the principle is similar. Speed without room to integrate. What's happening is just motion. The room itself is what becomes meaning. The speed of light defines how quickly events can communicate across the void, but it doesn't define how quickly you must understand them. You're allowed to linger, to loop back, to hear the same story many times until it settles. When you listen to the idea that nothing outruns light, you don't have to rush to agree or disagree. You can let the thought arrive, circle around it, tilt it in your mind, compare it with your own sense of time and change. Perhaps that's one of the quiet gifts of thinking about these things at night. The world around you is slower, fewer interruptions, fewer demands. The noises fall back, and suddenly there is room to look at something as abstract as a speed limit for reality and feel its emotional weight. It stops being just a constant in a textbook and starts becoming a kind of boundary you can lean your thoughts against. Inside that boundary, everything you care about unfolds: the warmth of the day, the glow of screens, the color of leaves in different seasons, the sound of someone's voice in the next room. Light ties all of those to your awareness at a manageable pace. Even its delay from the sun is the reason Earth isn't a place of wild, violent swings. The sun's energy arrives spread out in time and space, moderated by distance and atmosphere. What we experience as gentle warmth is the result of enormous power softened by distance and delay. The same pattern shows up in stories of discovery. A distant galaxy doesn't reveal itself in a single flash of insight. First, there is a faint smudge on a photographic plate or a weak signal in a radio survey. Then there are checkups, follow-up observations, better instruments, clearer images. Over years, the blurry patch becomes a spiral, then a collection of stars, then a clue about how the universe itself is structured. The light from that galaxy traveled for eons, and our understanding of it takes its own long path as well. So when we ask if there is a speed faster than light that we simply cannot see, maybe part of what we're really wondering is whether we can somehow outpace this process. Whether there is a way to know everything faster, to skip the incremental steps, to jump to the finished understanding. But just as a story loses something when you skip chapters, comprehension loses something when you rush past the slow unfolding. That doesn't mean we stop trying to go faster. We will keep building better telescopes, faster computers, more sensitive detectors. We will keep trying to see fainter objects and capture briefer events, to compress long processes into data we can play back in a few seconds. That's part of who we are, a species that sets records, pushes limits, asks what if and what next. Yet beyond all that effort, reality seems to be whispering a steady reassurance that it's okay not to keep up. The universe has been moving, exploding, collapsing, blooming stars and cooling relics long before there was anyone to time it. It will keep doing so long after we're gone. Our role is not to match its speed, but to dip into its flow long enough to notice a few things deeply, to leave behind a trace of understanding for whoever comes after. From that angle, the speed of light becomes almost like the turning of pages in a book that has been being written for billions of years. You cannot flip through all of them at once. You can only move page by page, beam by beam, signal by signal. Each one contains more than you can absorb in a single glance. You read what you can, you pass the book along, and the story continues. Maybe there are phenomena that, from some larger perspective, move faster than light in ways we don't yet have language for. Maybe someday we'll learn that space-time itself arises from patterns that don't care about distance the way we do. That connection, at the deepest level, looks more like entanglements quiet already together than like a race from one point to another. If that's true, the word speed might turn out to be a very local concept, useful only inside the slice of reality where we live. But even if that day comes, nothing about your evening changes. The sun will still set at the time you expect. The stars will still rise. The glow from your screen will still take a tiny but finite moment to reach your eyes. Your thoughts will still take the time they take, catching up to your feelings, rearranging your memories, weaving new ideas into your old ones. Whatever deeper structure there is, you live here, inside this layer, moving at this pace. And from here, the most honest thing we can say is simple. As far as we can measure, as far as every experiment has reached, no signal outruns light. There are tricks of perspective, illusions of pattern, shortcuts through geometry, but nothing that carries a genuine message has beaten that limit. The universe may have deeper mysteries, but this rhythm, the finite, steady speed of light, seems to be one of the foundations under everything else. There's a kind of comfort in that because it means there is a maximum rate at which surprises can arrive. No shock can come from truly nowhere in literally no time at all. Even the most sudden event in your life, the phone call, the breaking news, the flicker of headlights in the rain, is mediated by signals that obey this quiet boundary. There is always, in principle, a path you could trace back, a sequence you could reconstruct: cause, then effect, light, then sight, signal, then understanding. So, as you lie here, or sit here, or walk under whatever patch of sky you have tonight. You're sharing a universe with a very particular tempo. Photons are racing and drifting and scattering and coming to rest all around you, all the time. You don't have to feel their speed to be shaped by it. The warmth on your skin, the colors you see, the data beaming invisibly through the room, all of it depends on that same constant, that same calm limit. You are slower than light, much slower, but that slowness is what lets you turn speed into story. The universe takes its time sending you its messages. You take your time reading them. Somewhere between those two tempos, in the gap between what happens and when you come to know it, your experience of reality appears, not as a blur, not as a static image, but as a flowing, comprehensible tale. And maybe, in the quiet moments, that's enough. The question of whether anything is faster can rest for a while. Light is already fast enough to bring you the past, to outline the present, to hint at futures unfolding in distant places. You don't have to catch it. You only have to let it arrive, one small, finite, perfectly timed piece at a time, and allow yourself the luxury of being just slow enough to notice. A single orbit of a far-off planet around its star might take centuries of our time. No one human will see the whole loop, start to finish, and yet the planet keeps tracing its quiet path without needing an audience. A cloud of gas can take millions of years to fall in on itself and kindle a new star, slowly turning cold dust into light. Even entropy, that soft drift toward disorder, unfolds at its own unhurried pace, gradual, relentless, never rushed. Maybe that's one of the universe's gentlest lessons. It doesn't exist in order to hurry somewhere. There is no finish line it's straining to cross, no final moment it's racing toward. It simply keeps going, changing shape, breathing in its own enormous rhythm. We, on the other hand, often feel as though we're behind our plans, behind our questions, behind the endless stream of news and light and thought. We try to assemble meaning faster than the signals arrive. But the more we watch and listen, the clearer it becomes. Understanding takes time. Even the most beautiful ideas in science, the ones that quietly shift the way we see everything, rarely arrive all at once. They collect like faint photons in the mirror of a telescope, one, then another, until after long patience, a real picture appears, small measurements, repeated. A strange signal checked again. A question carried for years until the right experiment finally exists to ask it properly. None of that is fast, and yet all of it is progress. So perhaps what brings us closer to truth isn't speed at all, but a kind of stillness. Stillness in the way we look. Stillness in the way we wait. Stillness in the way we allow some answers to take longer than feels comfortable, trusting that they'll arrive in their own time, the way starlight does. Because the universe is not in a hurry, and it has never needed to be. It is still here, still unfolding, still full of light that hasn't yet reached us, of events already in motion that we have not yet seen. Signals are on their way across years and centuries and deep, dark gulfs. We don't need to chase them. We only need to be here, ready to notice when they finally touch the thin shell of air around our world and slip softly into our waiting instruments and eyes. Wherever you are just now, lying down, half awake, or simply letting your mind wander, I'm grateful you chose to drift through this with me. If this wandering has soothed you or given your thoughts a softer place to rest, you're always welcome to leave a quiet like, to subscribe, or to share it with someone who might need a slower kind of science tonight. Only if it feels right, and only in your own time. More questions will come. There will always be new puzzles just beyond the edge of what we understand. More light already on its way from places we haven't yet imagined. For now, it's enough that you were here, that you listened, that you let the universe keep you company for a while. If your eyes are still open, thank you for dreaming along while awake. And if sleep has already folded itself around you somewhere in the middle of these words, that's perfectly okay. That was always part of the plan. Whenever you listen, wherever you are in the world, may the distance between you and rest grow a little smaller, one slow, steady heartbeat at a time. Good night.